Ya, Assalamualaikum warahmatullahi wabarakatuh. For today's lecture, we are going to look into one example. How do we design a steel beam if we have a uniformly distributed load and also point load? Okay, so the example is actually example 9.2, which is you need to design a laterally restrained beam. What you have to do is you need to select and then you need to check the suitable beam section using steel grade S235, and it's given that the beam is set on 125 mm bearing. Okay, so here is the loading. It's given here that uniformly distributed load of 6 kilonewton per meter for GK and QK, and then you have 25 kilonewton point load at the center of the beam. Okay, first of all, you need to calculate what is the design action. So the design action uh, for here is written in terms of forces, the unit in kilonewton. You also can write in terms of kilonewton per meter. Okay, the equation is 1.35 GK plus 1.5 QK. Okay, since you have uniformly distributed load and also uniformly distributed load and also point load. So the point load is equals to 1.5 QK. Okay, next is you to calculate the design moment. So design moment MED for uniformly distributed load is equals to WL squared over A, and plus with the moment for point load is P AB over L. Since the point is located at the center, you also can simplify the loading equals to EL over 4. Okay, so from here we get that our bending moment, design bending moment is equals 133 kilonewton. From the equation, it's not given, the beam size is not given, so we have to select. Since we have known our MED value, then we can estimate what is the minimum required plastic moment resistance about major axis WPLY based on the equation for MPL RD. MPL RD here we can substitute into our MED value, and also Fy value is given as 235 since we are using steel grade 235. Okay, so you substitute into this equation and you get the value of WPLY in terms of millimeter cube. Then you need to uh, change the unit to centimeter cube by dividing with 1000 mm. So we get our MPLRD, our WPLY is equals to 566.8 centimeter cube. And then you refer to the appendix in the at the back of your appendix. So we can try this size as the WPL is equals to 774 centimeter cube, which is greater than the minimum requirement. Okay, so now we are going to check whether this beam size is suitable to support the load. Okay, the first checking is the classification of the section. You need to classify the flange. So here is the flange classification. So and we get 7.41, which is which is lesser than 9 epsilon. So it's okay. So it means here we get class class 1. And also for the web is also less than 72 epsilon. So all the section is belong to class 1. Okay, and then you check the resistance of the cross section. The first resistance that you need to check is bending resistance MPLRD. So for this side, we have known that WPLY is equals to 774 centimeter cube. So you substitute into this equation for class 1, 774 times 10 power of 3 since we changed to unit millimeter cube. Then times with Fy divided by gamma m naught. So we get that our plastic moment resistance is equals to 181.9, which is greater than our MED value than our uh, the and our section is adequate in bending. So the checking is pass. And then you have to check the shear capacity of the section. First, calculate what is the VED value. It's given that the VED is equals to WL divided by 2 plus P divided by 2 if we are using uniformly distributed load. Okay, so here from this solution is actually they using forces. So they just take the total forces divided by 2. So we get our VED value equals to 70 kilonewton. And then calculate VPLRD. First you have to calculate what is the shear area. AV. A is 57. This value is taken from the appendix. Then we get our AV value is equal to 647.4. And then we need to compare with the value of HW times TW. So the HW is 332.6. Since the value is greater, then you need to use this value. Okay, so this one, since the value is greater than 229, so we use this value to calculate VPLRD. Okay, so you put here, then you calculate your VPLRD and we get our VPLRD is equals to 359, which is greater than 72 kilonewton. Then it means that the section is adequate in shear. The checking is pass. Okay, so next checking is the shear buckling resistance. So you need to compare the ratio of HW/TW with 72 epsilon. Okay, so since the HW over TW, so this one is nothing, is 48.2, which is lesser than 72. So it means that there is no check on shear buckling is required. Okay. And then for flange-induced buckling, so you need to calculate the ratio of HW over TW against the limiting value for flange-induced buckling. Okay, so from this we get that the ratio of H over W is 48.2 and flange-induced buckling limit is 315.3, means greater than the limiting greater than HW over TW ratio. So the checking is pass. Okay, so next is you need to check the capacity of the section against web buckling. For unstiffened end support, it means that type C. So you calculate first, you need to calculate what is the KF value. Okay, since given that SS is 1 to 5 from the equation, since C, we assume that the bearing is provided at the end of the beam, so we can consider C equals to 0. So we get that KF is equals to 4.25. And then next you calculate FCR value, and we get FCR value equals to 793 kilonewton. And then you calculate M1 value. And to calculate M2, you need to assume which lambda that you want to use. So from here, let's say we assume that the lambda f prime is greater than 0.5. So M2 is equals to 23.5. Okay. So we get our M1 and M2 value, substitute into the equation of LE. But first, you need to calculate what is the LE value. Since the LE value is equals to 271.8, which is greater than SS plus C, so you need to use LE equals to 125. Okay, you need to take the minimum value. Substitute LE, M1, M2 into two equation of LY. And then you choose the minimum LY value. So from these two value, we get the LY value equals to 192.4. Okay, and then substitute LY value into lambda F equations, and then you compare with 0.5. Since the value that we calculated is greater than 0.5, so it means that the assumed value earlier is true. So we can proceed with reduction factor. And then you calculate L effective. At the end, you calculate what is the buckling resistance using this equation. At the end, we get our buckling resistance is equals to 237.6 kilonewton, which is greater than our shear force value. It means that the section is adequate in terms of wet buckling, so the checking is passed. Alright, so the last checking is to check the deflection requirement of the beam. Since the beam have point load, so you need to consider both loading. In deflection, we only consider variable action, which is QK value. Since here the QK is Newton 6 kilonewton per meter, convert it into Newton per millimeter. So you get the same value. And the QK you need to convert into Newton. The QK given QK is 25 kilonewton, so convert into Newton, it becomes 25,000 Newton. Then you substitute into the equation. The I value should be taken from design appendix, design data. And you substitute into the equation, so from here we get our deflection value is equals to 8.4 mm, and then compare with the limiting value, which is L divided by 360. Since the L is 6,000 mm, so we get our allowable limit is 16, so it means that the deflection check is passed. Alright, so that's all the design procedure for simply supported beam subjected to uniformly distributed load and also point load. Okay, so that's